Whoops, let me draw it like this. So the altitude is AH. And then angle BEH. So E is on CA, so that angle BEH is equal to angle C. What's the best way to do that? So that would mean that it's like the circumcircled BEH would be tangent to AC. So we want to draw a circle through B and H, and we want it to be tangent to the line AC. Yeah, what's the best way to do that? Let's think about this.
We need to draw the anti-parallel of CA in through H.
Anti-parallel of CA through H. Hold on one sec. So let me. I think I have a way to do this. Let me draw the angle bisector of this and see where it meets the perpendicular bisector. And then I want to draw the circle. Sorry. Oh no, that didn't work. Why? What was I thinking? Oh wait, yeah, not the angle bisector. I want to circle through B and H, and I want it to be, so basically it's going to pass through the midpoint of BH. Well, not pass through, but I want it to be the same distance from B. Okay, sorry, I'm going to scrap this. So what was your idea?
The anti-parallel, but I don't think it works. I don't know why.
Okay. Draw the circle orthogonal to, is that the circle with diameter CH? Centered at B. Okay. So you're saying I should draw this circle and then draw a circle orthogonal to that. And let's see, how do I do that? So I want it centered at B and I want it orthogonal. So I want, okay, basically, let me draw the circle with diameter BD. This would help me get a circle orthogonal. Okay. So I want that circle, right? Is it that circle? And then this point. Okay. All right, so that should be E. And then I'll do the same thing on the other side. Let me just check. So angle BEH. And this angle, there we go. Nice. Okay. All right. So BEH is angle C, and then I'm going to do the same thing on the other side. So let's draw the midpoint of BH. I want to draw the circle through C that's orthogonal to that circle. So I want to draw the circle centered at C through point J, and that will meet this at point F. And then I'll have what I want. All right. Hide that, hide that, hide that, hide this. Okay. So CFH is equal to angle B. And we want to let BE intersect CF at D. And then we want to show that DE equals DF. This problem actually looks really familiar. Any of you seen this before? So basically, BE is tangent to this circle, and CF is tangent to this circle. And we want to show that DE equals DF. So yeah, it has to lie on the radical axis of those two circles. So basically we want to show DK and H are collinear. All right.
BE squared plus CF squared is equal to BC squared.
Oh, really?
Yeah, I don't think it is useful, but it looks cool.
Yeah.
By
B squared,
points.
BH times B squared is BH times BC, and then you do it, and then you add the two. That is interesting.
So those three lines can form a right triangle. I mean, second.
Yeah. All right.
Oh wait, I think this is actually useful.
Oh, really?
So, yeah, draw the construct the right triangle with these three sides. So like, yeah,
Okay.
this circle and the other circle.
All right.
Then connect a BL and CL.
Does AH pass through it?
It should. Is it obvious? I'm not exactly sure.
Okay.
And then if that were true, which I don't think, I don't know if it is obvious, then this is actually, I think, a well-known problem. Like maybe some IMO or stuff. So like you take the arbitrary point on the altitude of a right triangle, and then like you take these points C and F, intersect with. It is kind of hard to explain, but it is basically the problem.
Okay, so basically, I think it's the, yeah, I think I remember. So it's like you pick an arbitrary point on the altitude, and then you see where A, B, and AC intersect these circles.
Yeah.
At E and F, and then you define D this way, and then you have to show DE equals DF.
Yeah. So basically, if it is true that L lies on the altitude, then we are kind of done.
We'd be done by that problem.
Yeah.
And since well, we know that BH times BC is BE squared, which is BL squared. So I think that kind of proves it, right? Because, well, actually, maybe not. Yeah, we have to show that A lies on the altitude, or L. Well, no. I think it's kind of obvious because we know AH is perpendicular to BC. And like if you drop the altitude from L to BC and you called it H prime, then we'd have BH prime times BC is BL squared, which is BE squared. So yeah, it's obvious.
So then we're done.
But by the IMO problem. Okay.
Yeah, but I'm not exactly sure how to solve that IMO problem.
Yeah. I'll just write that right now, and then we can go back to that at the end of the session. Because I think it's not that, I think it's like a somewhat difficult problem.
Yeah, it is not obvious at all, but
yeah. Let's just move on to the next problems, and then I can write this up later if we have time, and we can try more to solve it. All right. Oh, this is a fixed point type problem. Let me see. I think there was another. Okay. All right. I'll try this one. It's isogonal conjugates. So P and Q are isogonal conjugates. So I'm just gonna let P be a point, and then I'm gonna draw the pedal circle. This is usually how I like doing isogonal conjugates. Yeah, I like this definition better. So D and E are the projections onto A, B, and AC. So I'll just call F the other projection. So this is D, E, and F. Let me hide those. And I'm going to draw that circle. And then Q, I'll just draw the other points of intersection and take the perpendiculars. Does it ever say the projection of Q? I don't think so. G. Whoops. Okay, so this is Q. Let's draw all the perpendiculars in again. I'll draw that last one. Okay, the G is a projection of Q onto BC. Oh, there we go. U is a projection of G onto DE. This looks maybe a little familiar. Let's see. Let me read the chat.
Yeah, we did a similar problem before.
Okay. Oh yeah. So yeah, we could try the problem without moving the points. Okay, so does that? I think it's a well-known lemma that those. Oh no, they don't concur. Yeah, sorry. I have to move the points just to make the diagram look reasonable, I guess. Otherwise, it would. Sorry about that. Yeah. Projection of G. Okay, so this will be U. And then we draw the projection of P onto AQ. Okay, something like that. So this is L. And then U is the projection of G onto DE. And then we draw the reflection of L over UG. We call it K. Prove that UK passes through a fixed point. So yeah, there's a lot going on here. I'll draw this point.
I found the point, the fixed point.
Oh yeah, what is it?
Orthocenter.
Ah, interesting.
That is like the second thing I checked.
Ah.
But I didn't move points. I only constructed lines.
Interesting. So wherever P and Q are, it's UK passes through the orthocenter. And okay, so I won't move stuff around anymore. Just I just want to make the diagram look nice, and then I'm not going to move it anymore. That's hard to make a good diagram for this one.
I think a good idea is that if you can, let P be a special point, and according to that, we can somehow guess the fixed point. Like if you put P as the orthocenter, so maybe we can know that what point does it pass through. And similarly, let P be the circumcenter.
We could let P be the circumcenter, is what you're saying.
Yeah, that's normally how I do with paper and pen. Like let it be a special point, and we can guess the fixed point.
It's like you're saying we could say let P be the orthocenter, like using this. Yeah. Okay. Do you want to let P be the orthocenter P be the circumcenter right now, or
like if you want to guess the fixed point, then it's a good strategy.
Okay. P equals wait, why didn't that work? P Is that how you write it? Just P is the center of ABC? Or do I need like center of circle of ABC? Maybe that's why. Yeah. There we go. It's like that. So if that's true, so then the isogonal conjugate is the orthocenter, right? So D and E would be the midpoints. G is a projection of Q onto BC, so the foot of the altitude. Maybe the projection of, okay, so U would just be the midpoint of the altitude. L would be the projection of P. So L would be like right here. And
So
K
we know the fixed point must lie on the altitude of ABC, I think.
Yeah. So yeah, that tells it it has to be on the altitude. And yeah, like maybe from there we could.
Can you let let Q be the orthocenter, the center of ABC, and then we can know it. What is the fixed point by connecting that the UK with the altitude from me.
So wait, did you say you want to let Q be something?
Okay, so we let P be the center of ABC, and we know that the fixed point must lie on the altitude.
Mm-hmm.
So now let P be the orthocenter, and I think we will know what is the point.
Okay, so so triangle center ABC4. Okay.
The orthocenter, not the center of triangle.
Oh, the orthocenter of ABC, right?
Yeah.
I think, isn't this the notation for the orthocenter though? Triangle center ABC4?
I don't use GeoGebra that much, but why doesn't it work?
Yeah, I don't know why I didn't do it. It's weird. Let me see. Wait, P. I don't know if I typed something wrong. Yeah, triangle center. Yeah, I must have just typed something wrong. Let me try it one more time. Oh, you know what? Oh, there we go. All right, so if we make P the orthocenter, and D and E are the projections, so those would be the feet of the altitude. And then G would be the projection of Q. So Q would be the circumcenter. G would be the projection onto BC, so that would be the midpoint of BC. And then U is a projection of, okay, so U would be the midpoint of DE, because we know BDEC is cyclic. And then L is the projection of P onto AQ. So the projection of the orthocenter onto AO. And K is the reflection. So wait, is it well known? That would be K. So we want to show UK. So yeah, as long as, since K is already on the altitude. So yeah, K and P, is it clear that K and P are the same point? Is that obvious?
Maybe it seems like so. So then the fixed one is the orthocenter of ABC.
Yeah, I think it's obvious that K and L are reflections across UG because it's well known that AK is twice QG, right?
Yeah.
I think it follows from that.
So yeah, this strategy also works if we don't use GeoGebra. So we did not cheat, but we found the point.
Okay.
So
See you next time, Jamin. Jamin has to hop off. Okay. So yeah, I kind of like that. So that would kind of prove that it has to be the orthocenter. Yeah. All right. So then we would know that it has to be the orthocenter. So now we could try solving the problem. All right. It's interesting. All right. This is interesting. This seems hard. To me, this looks hard. What do you guys think?
You label the orthocenter. Yeah, I think it's a little hard to, but we should draw the orthocenter and try to prove it first.
Okay.
It doesn't look impossible.
All right. A, B, C, 4. Yeah, I should probably call this something different. Call that H. Call it L. Or no. Call it R. I think that should be okay. Call this H. H. All right. I like that diagram. I'm gonna get a little snack. I'll be right back. Right. Let's try out some stuff. So, yeah, what property do we want to use about point H? I don't think U, P, and F are collinear, right? Yeah. Maybe JH is perpendicular to AB. Yeah. Yeah, these are like cheese crackers with peanut butter in the middle. They're very tasty. Sorry. Yeah, they're really cheap. Like food prices have been going up with inflation, but somehow these crackers are still really cheap. You can get 8 of them for $2. 8 whole packages of these for $2. All right. So yeah, what do we want to use about the orthocenter? Should I like draw the altitudes from B and C in? Let's see.
I found something. So mark the center of the P2 circle.
All right, so that's the midpoint of PQ.
Yeah. I thought that MH is perpendicular to DE.
Oh, not in this picture.
Yeah. Okay, I think I made a mistake.
It's all right. H, J, and M. I was wondering that too. I don't think so. No. All right. We have animal joining. Animal. Thanks for joining. So yeah, this is the 4th problem we're on. It involves isogonal conjugates. And it's like a fixed point problem. Like you want to show UK passes through a fixed point, but we figured out that point has to be the orthocenter. So we want to show that UK passes through the orthocenter of ABC. So yeah, I don't know if we want to draw the altitudes through B and C. Maybe A. Oh, are C, J, and H collinear? No. So yeah, what do we have to use something about point H. I'm not sure what. I think I might rather just draw in like these 2 points. Steiner line. Sounds like an interesting idea. Oh, I'm not, I would never use barycentric coordinates. I do not. I think we did one problem similar, like using some fact about isogonal
I think
conjugates.
it was a like a perpendicular problem, I think.
Yeah, I forgot what it was.
Yeah, you uploaded it on your channel, remember?
Yeah, if you guys can find it on YouTube, yeah. Let me know. Let's see. I'll spend maybe like 10 more minutes on this, and then if we don't get anywhere, we can move on. Yeah, it's weird that it's like not symmetric because you're taking the projection of P onto AQ. What if I took the projection of Q on AP? Like I wonder if I could create some symmetry here. So it's not true that PH and A are collinear, but oh, interesting. Let's check that out. Yeah, let's see if we can find the anti-Steiner point. So basically we take that line and we would reflect it over the three sides. So it would be this point right here. And maybe there's something special about that point.
I think it lies on the circle with diameter AP.
Diameter AB.
AP.
AP. So interesting.
Can you check if those point lies on the radical axis of BE and C? Wait, let me see. BE and CD, I think. Can you check?
BE and CD.
Yeah. Do they lie on the radical axis of these two circles?
Or so do you mean this and this, or Which two circles? And at what points?
The circle with diameter BE and circle with diameter CD.
Okay, where those are the diameters. Okay. So not BN, but BE.
Yep.
Okay. All right, so
looks like UL also passes through the Steiner point, the anti-Steiner point.
UL passes through it. This is really interesting. Okay, so Khan was saying draw the circles with diameter BE and CB. And so were those the two circles you were talking about?
Yeah.
Interesting. Yeah, it looks like it's the radical axis of those two.
Okay, so maybe it's a good way to do it.
What made you think of that, to draw those two circles?
Actually, if it is the radical axis, then it will also pass through the orthocenter of AED. Like there's a very famous thing. There's a very famous problem when you learn about radical axis is that given triangle ABC, and then you take the 2 point D and E on AB and AC, and you label the orthocenter of ABC and ADE. Then the line connecting those two orthocenters is the radical axis of the circle with diameters B and CD.
Ah, so I could also draw the orthocenter of ADE.
Yeah, and that is called the Steiner line of the complete quadrilateral. So yeah, it's a problem that I often use.
That is like the proof of Gauss line also.
Yeah, and I even used it in the VMEO 2022 that I participated.
This year's VMEO.
Yeah, this year VMEO, which
I looked at the problem, and I solved it using one projection and a midline, I think.
Oh. Yeah, I remember about the midline. I did use that.
Mm-hmm. There's something like it on VMO.
Yeah, we did on the session too.
I'm gonna have to go. I'll be honest, I haven't watched my own videos in a long time, but I will have to go back and watch them.
Yeah, maybe just the one that you know have a really good impression on.
Yeah. Yeah, I think I might have forgotten to send the GeoGebra files last week, but I think I still have them, so I could send both this week and last week. All right. But yeah, this is a super rich configuration with the anti-Steiner point, and then these three are collinear, and then these all on the radical axis.
I don't know if it will help any, but
wait, I think this problem is super easy. I think.
Really?
It's not really hard at all. Can you just?
I will let you speak.
Yeah, sorry. I'll just present my. Did you solve it, Stefan? Maybe
no, I just wanted to say something, but I don't think this is important at all.
Okay, so let me just try real fast. So can you just delete a couple of things that we don't
Yeah.
need. Maybe just keep the points from the original problem.
Okay. All right, and then we'll add stuff in. So I'm gonna. Do you want me to draw point S?
No. And delete the two circles with diameters. I think we will need them, but we don't necessarily draw them out because they're messy.
Okay. I forgot what point Z was.
Point Z. Nah, just delete it. We don't need
Sorry. Let me see
Okay.
what I could probably hide. Should I hide these? Is that everything?
Yeah. So can you label the orthocenter of AED?
Sorry, one second. AED. Okay.
AED, yeah.
Let me see if I think it might be this point right here.
Okay, so
let me call it X.
So we have an easy claim that ADLE is cyclic.
Okay.
They lie on the circle with diameter AP.
Okay.
So we have X and L are they are reflection about B. Yeah, you can draw that circle.
X and L are symmetric about D.
Yeah. So I think we can prove that X, K, and U is lies on a line, I think.
Okay. So X, K, and U are collinear.
Yeah. So we just need to prove that X, H, and U is collinear too.
How do you know that X, K, and U are collinear? Oh, is it because by homothency? Because since L is the reflection.
Yeah.
Okay.
Maybe just an angle chase. It depends.
Okay.
Oh wait, actually, I didn't prove that X, U, and H. I just only proved X, U, and K. Maybe somehow we can prove that U lies on the radical axis. We have proven that K lies on that radical axis. So we need point U too, I think.
Okay. So yeah, is it obvious? So if we take L, if we reflect it over UG, we get K. If we reflect it over DE, we get X. Is it obvious that X, U, and K should be collinear? Oh yeah, because this is like the perpendicular bisector. Well, yeah. It's probably not hard to prove that X, U, and K are collinear. All right. Okay. Okay, so basically you're trying to show that H, U, and X are collinear. So basically so KU and X all have the same power with respect to those two circles, right? So you need to show it. I think if we can show H has the same power with respect to those, that would solve the problem, right?
That is easy. So we just need U, only U.
We just need point U, is what you're saying.
Yeah, because point H, you just drop the two altitudes, then you can calculate the power. Very easy. Similar to X. We only need U left, because if we can show that U lies on that line, then we can also show that K lies on that line.
Okay. I wonder if let's see. Let me think about point U.
Draw the perpendiculars from B and C to line DE.
B and C to line V. But I wonder if it's obvious. So I'm going to do that right now. But is it obvious that U lies on KX? Because basically, if you take L, if you reflect it over UG, you get K. If you reflect it over DE, you get X. And then this is like the perpendicular from G.
So maybe we can do an angle chase. We can prove that angle LUX plus angle LUK is equal to 180.
Like if we can show GL equals GK, I think that solves it. Hold on one sec. So yeah, basically we need to show GL equals GK. What was the angle chase you just said?
I proved that they are collinear by showing KUL plus LUX equals 180.
Okay.
Because they are equal to 2 times JUL plus 2 times LUE. And that is 90 degrees times 2 equals 180.
Okay, so that like solves the problem, right?
No, it only shows that X, U, and K are collinear.
But by the lemma you said earlier, X and H both lie on that radical axis, right?
Yeah, but we don't know if XH and XUK are the same line. So the thing is, we need to show that U lies on that radical axis.
May I say something?
Yeah,
I think that I found something that simplifies not those two.
Okay.
You should intersect those perpendiculars with the DE.
Oh, whoops. Okay. So
because it is like only left to show that UK has the same power.
yeah.
So when we construct those 2 points, we will actually have 2 powers. So we need to prove that UD times UB1 is equal to UE times UA1.
Okay, interesting.
But that is equivalent to showing that UA1 over UB1 is equal to UD over UE.
Okay, and then using these parallels, that's BG and BC, right?
So we can get rid of those 2 lines, and we just want to show that DU over UE is equal to BG over GC, which looks like something that could be done.
Yeah, that looks really doable. Let's see. I think that might even be the lemma that we did in the previous video, something like that. Geo King said DE is the external angle bisector of UKL. And so x, k, and u are collinear. Is that another way to prove those are collinear? Yeah, I think, have we solved? I'm a little confused, but okay. So so the lemma, first I'm going to write out that well-known lemma that you said. So the lemma says that x and k both lie on the radical axis of the circles with diameter BE and CB, right?
Yeah. Maybe you can.
Is that the lemma?
Yeah.
Okay. BE and CB. So yeah, I'll say let X be the orthocenter of ABE. All right.
Just so I think I'm close to proving that those two ratios hold, which I said earlier.
Okay.
So we basically need to find similar triangles, and in this case they will not exactly be similar, but it will do the job. So consider triangles BQC.
Okay, so BQC, this one?
Yeah. And triangle DGE.
Okay. So they're not similar, but their angles like add up to 180 kind of?
Yeah. And
Okay.
I'm not, I think it must be an angle chase to prove that those add up to 180. But if that were true, then that would be sufficient, since you could, to be like more rigorous, we could like construct the like orthocenter of one of those triangles, and then those are similar, and then we have the ratio. So basically, this would be enough.
Yeah, I feel like there should be a word for that. Like two triangles, they're not similar, but it's like the angles add up to 180 and those two sides are in the same ratio. I kind of know what you mean. So
But, I don't know the angle trace at the moment.
So can you recall one more time that what do we need to prove those two angles that equal which angle?
he wanted to show that du over ue is was it cg over gb or bg over gc? Yeah,
BG over GC.
okay.
So which angle are you gonna prove that they adds up to 180?
BQC and BGE. Let me check if that's true. Yeah, they add up to 180.
Easy angle chase. We can do it by observing that DGE is equal to DFE. DFE is equal to DBP plus DFP plus PFE. And it is DFE is equal to DBP is equal to QBC.
That's nice. I like that. So I'm gonna write that.
I missed that BDPF and CFPE are cyclic. It is an easy angle chase.
Oh yeah, I like that. So that's DFP plus EFP. And that's DBP plus so ECP. And that's angle QBC plus angle QCB, which is 180 minus angle BQC. Okay, let me, just gonna do it. Let's see. Yes. Okay, so the X and H lie on that line. U okay, so well, KU and X are collinear by symmetry because L, if you reflect it across UG, yeah, I mean, basically, like this is a rectangle, right? So we call this Y. Because Y so UYLJ is a rectangle. So like if you reflect L across both those, it's going to be collinear with U, right? So X, U, and K are collinear. Okay. So yeah, I'm just trying to make sense of all this. And then we could show, I guess we could try to show U lies on DE is the external angle bisector of UKL. Yeah, XK and U are collinear. OKU and L, you're saying. Oh, yeah. So yeah, I see why X, U, and K are collinear. is it easy to show that U lies on the circles with diameters BE and CD?
You mean on the radical axis?
Yeah, on the radical axis.
That is the thing I proved.
Yeah, like the two altitudes that Stefan drew, and then he hit it.
Okay, so that's where we want to use what Stefan was saying.
Yeah.
Okay, so okay, so let me call these something different. I'm running out of letters here, but do we use U, A, B, C, D, E, F, G, H, J, K, L, M, and N? I don't think we have in this picture. M, N. Okay, so basically we want to show that UE times UM is equal to UD times UN, and then we do kind of what Stefan said. So so UM over UN is BG over GC, and then okay, so basically, is BDEC cyclic? I don't think so. But you're saying that, so you're saying that because, wait, did I hide this? You're saying that because DGE is 180 minus QBC, that proves that BG over GC is DU over UE?
Khan also noticed that that isn't complete. So
Okay.
when we like complete BQC, like draw its own orthocenter, then also we have two more angles, and those also have to be equal. But it is not different since it can be angle traced also.
Okay, so did you want to show like BQG? So yeah, I'm trying to think how it works. Maybe mark GU intersects FGD.
Yeah, that's right. And then we can prove that maybe let GU meet the circle like Geo King said. Yeah, OD and QBC similar. Trying to prove that.
Okay. So this is O. And then we try to show ODE is similar to QBC. Yeah, I like that. I feel like so this means that DOE. Okay, so yeah, it's probably an angle trace to show that DOE is similar to QBC. And then once we know that, it's just true by similar triangles. Okay. So this implies DOE equals BQC. BQC. And let's see if we could show some of the other angles are equal. So angle ODE is angle OGE. And QBG is QIG. So we want to show QIG is basically we want to show triangles GUE and QBG are similar.
I think we can show, because we have angle ODE is equal to angle UGE.
Mm-hmm.
So and we also have QBC is equal to PBD.
Oh, okay.
So we're trying to put a PBD is equal to UGE.
Yeah.
So we have PBD is equal to BFD, because PDBF is cyclic.
Okay.
And then finally, we have BFD is equal to UED, because DFGE is cyclic.
PFD is equal to what?
We have DEG is equal to DFB.
DEG equals PFD.
No, DFB. So maybe I'll type it out for you.
Okay. That was interesting. A lot of cyclic quadrilaterals. Okay, so that would show that X, yes. So then we would have X, so that would show that U lies on XK. No, sorry, that would show that U lies on XH. So then X, UH, and K are all collinear. Yeah. Okay, so I'm going to copy what Khan just put. Whoops, let me change, get rid of this. All right. Oh, nice. Finally get to finish school and move on, or for the rest of the year at least. So, okay, so QBC is PBD is 90 minus DPB is 90 minus DFB is 90 minus DEG. Ah, that's fair. Which is OGE, which is ODE. So then we have DOE is similar to BQC. And that means that DU over UE is BG over GC. I think that should be D. What is happening here? Oh, whoops. That's what went wrong. Triangle. Once we know that, which is mu over un. So then du times un mu times ue. That means that u lies on the radical axis of the circles with diameters BE and CD. And that means that X, U, and H are collinear. Which means that X, U, H, and K are collinear. There we go. And so that means that UK passes through the orthocenter K of ABC. Wow, I'm really impressed that you guys figured this one out. It was that key lemma right here. All right. So you got to do a lot of geometry during the summer. I'm jealous of you guys. I wish I could take off during the summer. I don't think my boss would be too happy about that. All right. Okay, so we have like 7 minutes left, probably enough just to look at another problem. This one could be really easy. So this one was all the way back in 2006. We probably won't solve it, but it's kind of interesting actually just figuring out how to construct the diagram. So O is the center. And then we have a point such that the line perpendicular to OA. So basically we draw the line OA. And it looks like someone else just joined. I'm not sure who. Hi, Anurag. So we have about 5 minutes left in the session. So we've been going for about 3 hours. So sorry you came in towards the end, but maybe next week, yeah, if you come earlier, we'd have more time. 49 people for Vietnam team selection test. Yeah, Vietnam is really, really good. It's impressive. 28 people for Serbia. Okay, so we want a point on arc BC so that when we draw the perpendicular to this, okay. So it's a point on the arc so that when we draw the perpendicular, A1 is the midpoint. So yeah, how do you figure that out? This is an interesting question just to figure out how to draw it. So like if we take a point on the arc and we drop the perpendiculars, we want
the symmedian, like the symmedian line.
Oh, it's just the symmedian line?
Yeah, like the points on the arc that makes ABDC a harmonic quadrilateral.
Okay. So let me draw the tangents.
you should move point A because the tangent is going to be like at infinity.
Okay. Oh yeah, I think I actually did this like in the proof of the symmedian theorem. Like if you draw the anti-parallel to BC through D, basically, yeah, like if you look at this circle right here, you can show like by an easy angle chase that like, yeah, let me make it smaller. It's like an easy angle chase that DF and this point are collinear. And so, yeah. So basically, they just want to show that, okay, so then this problem's trivial because it's just saying that we want to show that it's just the Gergonne point of this triangle, right? Yeah, it's trivial, right? They're just saying that these three lines are concurrent. Okay. All right. So yeah, that's kind of too easy. I'm just curious. Let's see what the other prompt said. This is going to take a little while to construct. There was another fixed point problem, I think. I just didn't do it. Let's see. This is VMEO problem 2. So yeah. Maybe I'll just copy it into the GeoGebra, and then if you guys want, you can just try it after the session. So let's see. Oh, I think these kind of problems are hard. Interesting. All right, so I'm going to stop here since we're out of time. Thanks everyone for joining. We had a lot of really cool proofs, and I'll take a look at the problem that GeoKing just said for next time. But yeah, I was really impressed with what we were able to figure out this time. So for those of you watching on YouTube, if you'd like to join us in the future, feel free to email me at mgreenby801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks for watching and have a good day.